Hello, my name is Bill Winston. I'm a GIS analyst here at Washington University, and the purpose of this talk is to introduce you to GIS concepts, to help you understand what GIS is used for and why it's an important technology. GIS stands for Geographic Information Systems, and this technology is widely applied to visualize data, perform spatial analysis, and effectively communicate results. You may not realize it, but it's very likely that each of you are already regular users of GIS. Now, GIS impacts our lives in many ways. Federal agencies, state governments, and many corporations use GIS for managing resources, connecting citizens with public information, risk assessment and disaster planning, and for delivering services and business planning. When you go to check out at the local Schnucks grocery store, they sometimes ask you for your zip code. Have you ever wondered why? Zip code is a very innocuous piece of information that most people are willing to share, and it gives the business spatial information about you. How far did you come to shop here? Are you from the neighborhood, or do you live in an area that's not currently served by one of their stores? By collecting and analyzing zip code information on their customer base, Schnucks can decide whether to expand into a new region or determine where to target marketing efforts. This is a very simple example, but it illustrates how useful spatial information can be. Now, most of us are familiar with visually processing spatial information from our experience looking at maps. Printed maps are static examples of a GIS, and we can understand some basic concepts by looking at a historical map. This is a digitized copy of the 1904 World's Fair map. This map was created to help fairgoers find exhibits of interest, determine the best way to get from place to place, locate a snack, find the nearest restroom facility, or even locate the garbage crematory. Let's take a closer look at this analog example of a GIS. In the context and language of a GIS, this map basically shows us three different layers of information. Buildings are represented by polygons showing the structural footprint, and they're color-coded by industry, shown by the pink polygons, or region or purpose, shown by the orange polygons, such as restaurants, hotels, and cottages, and all of the buildings are labeled. Transportation routes are drawn as paths, roads, or rail lines. Water features show the outlines of lakes and lagoons. Now, each of these feature types would be stored digitally and represented in a modern GIS as individual vector data layers. These layers would only contain a single geometry type, point, line, or polygon, and the features in each layer would share a common set of attributes. Attributes are the supporting information that makes GIS data so useful. In the case of the buildings layer, the attributes could include the building name, its address, and perhaps its purpose. The attribute values can be used to query the data set for particular features of interest, to control symbology and labeling, and could also be used for analysis. In addition to the primary data layers, the map includes an indication of land cover based on color or symbology, and also some common map elements, including an index table and spatial reference grid, a north arrow, and a scale bar. Now, this map is a static snapshot of these data sets. Many modern geographic information systems are designed to be accessed dynamically and enable the user to interact with the underlying data. Digital maps have improved upon the scale of coverage and level of detail available to the user. This example is from a screenshot from MapQuest showing the Washington University campus. This map shows some building footprints, roads, and water features, much like the World's Fair map. But in this case, the user determines the spatial extent and area of interest. Controls allow users to pan and zoom, and also to choose a base map option, showing either streets as this one does, or an aerial view. The primary purpose for the MapQuest website is to enable users to get driving directions from one place to another. This can be accomplished by entering a starting and ending address, and then the underlying proprietary network data set is used to determine the shortest route between the points. In this case, I have requested directions from Wash U by entering 1 Brookings Drive to the Gateway Arch. Now the map shows my complete route, connecting my origin location to the destination. This solution shows a route that does not follow the most direct path. At the time I created this example, Highway 64, the one that runs down the middle of the map here, was closed due to a major construction project. The MapQuest database was aware of this and routed me around the obstruction on an alternative route. Another example of an online GIS is Google Earth. Here we can see the WashU campus in an aerial view that's familiar to anyone who has used this application. Google Earth opened a new perspective for many of us by allowing us to go anywhere in the world for a bird's eye view. What was the first thing you did when you tried Google Earth for the first time? For many of us, we started by asking Google Earth to find my house. I'm sure you noticed many things that were expected, but you likely also saw some things that you were not. New understanding comes from looking at things in a different way, and Google Earth certainly facilitates this. But there's some underlying reasons that our use of Google Earth starts with such a simple request. One major outcome is to establish trust. By asking Google Earth to show you someplace that you already know, you can verify that Google Earth is trustworthy. If it knows where your house is, then we can have some confidence that areas we are not familiar with are also reasonably accurate. Another issue is the timeliness of the data Google Earth is showing. Has something recently changed in my neighborhood, and is it reflected in the imagery? This gives us an idea of how current the data are. Now this imagery is an example of the second type of data that we typically see in a GIS, and that's raster data. Raster data sets store imagery and other continuous data such as temperature, land use, or population density. You can think of raster data in terms of a light bright, an old toy that you might be familiar with. This toy was basically a gridded board with colored pegs that allowed kids to create designs by placing pegs in the holes. Pictures are basically raster data sets that use colors in each grid cell to create an image. Here's a low-resolution example of someone that we might all recognize. Higher resolution photographs are created using smaller grid cells. In GIS, the raster data set is used to represent continuous phenomenon. In the case of Google Earth, it's an aerial picture of the Earth's surface, but sometimes it can be used to represent other information, such as the United States, and the cell values in the grid would be unique for each state. Now let's get back to our online examples of GIS. Another important feature of Google Earth is the ability to add additional layers of information to the display, including in this case places and roads. As we saw on the World's Fair map, these are vector data sets used to represent discrete features using points, lines, or polygons, and they usually include other attribute information such as business or street names. MapQuest and Google Earth are both online examples that illustrate a few important GIS concepts beyond their data types. Access to seamless data sets. This application can show me an aerial view of any area on the globe. Additionally, I can display other data layers that are spatially referenced, including data that I might create myself. The ability to combine data from different sources. We can display vector and raster data sets together, and because each of the layers has its own spatial reference system, they align properly. Dynamic display. This means that the level of detail shown on the screen can be dependent upon the spatial extent, or the area shown in the window, and that's controlled by the user. Control of layer visibility. Users can determine which data layers are of interest, turn them on or off, and also control their symbology. We also have the ability to query the underlying data, and we can do that based on location or attributes values. This is a very important GIS concept. For instance, I can ask the GIS to show me all Starbucks restaurants, or I can ask it to find the closest one to my current location. Now, I'm sure that most, if not all of you, have interacted with MapQuest, Google Earth, or a similar app on your smartphones. If so, you can consider yourselves experienced GIS users. These examples are lacking some aspects of true GIS and thus could be considered consumer-grade GIS. More functionality is available in professional applications like ArcGIS, and I'll mention some of those shortly. But first, let's talk about why you might be interested in using a GIS for data visualization. Sometimes it may not be clear that an issue has a spatial component. For example, let's start with a simple question. If you're out at a restaurant and you want to order a carbonated soft drink, how do you ask for it? Do you request a pop, a soda, a Coke, or some other term? If we surveyed the entire WashU community, we might come up with a table like this. Mildly interesting perhaps, but the general response would likely be ho-hum. But suppose we also ask for some spatial reference point. How about the zip code of your hometown? As we discussed earlier, this is an innocuous piece of information, but it does allow us to put each response into a useful spatial context. In a GIS, we would join the survey results in this table to an existing set of zip code polygons. These vector features are polygons that show the shape of zip code areas, but may not contain attributes other than, as shown in this table, an FID, the shape, area, perimeter, and zipnum attribute fields. Now the join process uses the 5-digit zip code from the survey results to link to the appropriate polygon based on the value of the zipnum field. Now, once we do this, we can look at these results in a whole new light. That's exactly what the folks at popversussoda.com have done. This map shows all of the zip code polygons in America, color-coded as shown on this triangle-shaped legend. Pure red, green, or blue indicates an overwhelming favorite for that particular zip code, and any areas with an intermediate shade indicate a blended response. So viewing our results as a table does not reveal the regional clustering that's so obvious when we display these data using a spatial context. But why do these patterns exist? Actually, they could be the result of regional preferences, historical or cultural biases, even brand loyalty. After all, Atlanta is the home of Coca-Cola. It's not clear, but presenting the data in this way gives us a new perspective. And I think by now you should be detecting a theme here. One of the core functions of a GIS is data visualization. Mapping your data enables qualitative visual analysis that connects people and things to place. Location is very important, but so too are the attribute information associated with each location. Here is a very early example of applying qualitative visual analysis to a public health problem. John Snow was a doctor in London in the 1800s. He was working on a cholera outbreak in 1854 when he decided to use a map of the Soho neighborhood where the outbreak was occurring to plot the locations of people who had died from the disease. Let's take a closer look at his map. Once he had marked all of the deceased addresses by adding points to the map, he also added locations of all the pumps providing public drinking water using an X. You can see there are a number of them located around the area. He could clearly see that most of the deaths occurred in close proximity to the pump that was located near the center of Broad Street. Using this insight, Dr. Snow lobbied to have the pump disabled, and this led to a reduction in new cases. Further investigation revealed that the water supply to that pump had become contaminated and was spreading the disease to anyone who drank from it. If Dr. Snow had access to a modern GIS, his workflow, or the steps that he used for this analysis, would have looked something like this. He would first start with a street layer for the Soho neighborhood. Each line segment in this layer would have attributes including the street name and addressing information, such as the range of street numbers that occurred along the segment. To the streets layer, he would add a set of point features showing the locations of all the public drinking water pumps. This data would likely come from the municipality's water department and would have been collected as a set of coordinates using a GPS device. Next, Dr. Snow would have obtained a table of addresses and names for all of the people who had died from cholera within the last month or two. He would then use a GIS function called geocoding to automatically create a point on the map at each of the addresses in his table. Now, with all these layers in place, Dr. Snow could take advantage of a geoprocessing tool to quantitatively analyze relationships. Our visual analysis revealed a clustering around the Broad Street pump, but we can be much more precise with these modern tools. Our modern GIS will allow Dr. Snow to associate or spatially join features from one layer to features in another. So we'll use the spatial join function to identify the closest pump to each depth point, and then the tool will add an attribute field to the pump data set that contains a count of how many depths are closest to that pump than to any other. This data can be displayed as a table in this case, or it could be used to control the symbology of the pump symbols. Now, using some cartographic skills and the results of his geospatial analysis, Dr. Snow could create a map that shows the original data and the results of his analysis, and he could use that map to quickly communicate his findings to city leaders. He could draw their attention directly to the Broad Street pump using a unique symbol like this, or he could use graduated symbol sizes based on the count attribute to illustrate the relationship graphically. The key takeaway message here is that maps enable qualitative visual analysis and can communicate effectively. A GIS facilitates map creation and also enables quantitative spatial analysis. So to summarize, a GIS is a collection of data, computer hardware and software, and a skilled user. And these can be applied to data visualization and analysis problems. Users add different layers representing various real-world features, and these layers include a spatial referencing system that correctly aligns them in space relative to other layers. It is also possible to add non-spatial data, such as survey results, as long as we can link them to some existing geometry like zip code areas. We can use the underlying attributes of our features to control how the features appear, or use those values for analysis, and then to create informative map products that display our data and results. Finally, there are spatial analysis tools like geocoding, spatial and tabular joins, and many more that enable complex investigation of the spatial distribution of features and their attributes, either in the same layer or among two or more layers. These tools are what sets a professional GIS application like ArcGIS apart from more consumer-grade applications like MapQuest and Google Earth. So now let's concentrate on how GIS could be applied in the field of social work. Community assessment and asset mapping. Sometimes the most important application of a GIS is to help people understand their own neighborhood. What services are available nearby? Are there barriers that make it difficult to take advantage of current resources? Are there better ways to deliver those resources? Visualizing survey results by converting response tables into maps that show distribution. This can be very important to help you understand the scale of an issue and to display such information along with other existing data sets. Now, hotspot mapping uses incident data as points or incident rates as polygon areas, and clustering analysis to identify areas where incidents appear to be more focused, a so-called hotspot, or more dispersed, a cold spot. This sort of product is common for crime analysis projects. The locations of hot and cold spots can be compared with data from other layers, such as per capita income, age or educational demographics, land use characteristics, streetlight density, etc. This allows us to look for clues as to why the clustering is occurring and to propose ways to address the problem. We can also use census data to understand demographics. The U.S. Census Bureau collects, compiles, and distributes a wealth of free information at a range of scales. These data cover all aspects of age, race, and socioeconomic status and offer a regularly updated source of detailed information about the people living in the U.S. Social scientists use this information to understand how it impacts local conditions, how public policy might be changed to help improve a situation, and where those policies should be targeted to have the greatest effect. We can also use GIS to communicate results and connect with users. As you have already seen, maps can communicate very quickly and effectively. In many cases, a map is more efficient at conveying a message than any other medium. So what are some of the specific questions that you can answer with a GIS? Here are a few examples. What areas of a neighborhood are more than a 5-minute walk from a bus stop? Perhaps you're working with a population that predominantly uses or needs access to public transportation. This type of analysis will help you determine areas in the neighborhood that are currently being adequately served versus those that need better access. What is the best, either shortest or fastest route for delivering services to constituents? A GIS can solve complex network routing problems, such as what is the shortest path, either in miles or time, to visit a list of addresses. How about demographics? If you can identify a common set of demographics that make up your service population, then you can use GIS to find other areas that share the same set of demographics. This data could be used to target new clients. On the other hand, if you're an agency or organization that depends on a donor base, you could determine a common set of demographics for people who tend to contribute, and then target areas with similar characteristics in future donor drives. You can also ask other criteria-based questions like, do I live in a food desert? This type of analysis identifies areas that meet certain criteria. In the case of food deserts, all existing food sources would be identified and mapped. An analysis is then performed to find areas that are outside of some distance or time constraints that you would define. Those areas could then be targeted for additional services, or local businesses might be lobbied to expand into the underserved area. Now, these are just a small sample of the ways that GIS can be applied to issues of importance to the social sciences. Now let's look briefly at a couple of specific projects from past students in the Master of Social Work program. Here's a study that looked at the correlation between physical disorder and the prevalence of crime. More than 600 properties in a St. Louis neighborhood were classified using Google Earth Street View to remotely evaluate property conditions. An attribute was added to a set of building footprints so that property could be symbolized in this map based on the appearance of neglect that was noticed in Google Earth Street View, such as boarded windows, unkept lawns, etc. Crime incidents were also plotted, and an analysis was performed to determine if a relationship was statistically significant. Another project involved characterizing the demographic profile of people living within the 100-year floodplain. In this region, there are over 700,000 residents living in these low-lying areas near rivers and streams. These areas are prone to flooding and require residents to purchase flood insurance. The researcher used floodplain boundary areas obtained from FEMA and demographic data from the U.S. Census Bureau to examine the socioeconomic profile for residents that were living in these areas. So now that you know what GIS is, I hope that you have come to the realization that you are more familiar with this technology than you thought. If you're interested in learning more, our website can connect you to resources, including access to an evaluation copy of the ArcGIS software. Click on Current Students and Resources, or use this web address for more information. ArcGIS is one of the most heavily used GIS applications in the world. Washington University has a site license that enables us to offer a one-year fully functional student evaluation edition of this software to any interested student. The software is a Windows-only application, but it can be installed and run on a Mac with some extra effort. So finally, I hope this talk has given you a new perspective on GIS and how useful it can be. Thanks for your attention. Please contact me if you have any questions.